Okay, I want to do a few examples of linear transformations. Specifically, I want to just to get some of the basics. I want to look at some of the following questions. So let me say it this way: look at the following questions, just to get the basics down. First, so I should say, given a transformation t of x equals y, one, what dimensions? So t goes from what dimension to what dimension? So the idea will be to identify these. Question 2 is, what is the matrix of t? These are pretty straightforward once you write down the formula. And then the one that could be a little bit harder is, what is the image of t? Okay, so I want to look at these three questions for just a few different examples. So here's an example. Actually, this is the example from last time. So let's call this matrix, this transformation t sub a. And it's defined by this formula we gave last time. So I plug in a pair x1, x2, I get out a pair 5x1 plus 3x2, 3x1 plus 2x2. We call that y1, y2. And pretty quick, we answered the first two questions already in the last video. So clearly the input is two-dimensional and the output's two-dimensional. And t of x is a times x, where a is the matrix 5, 3, 3, 2. Okay, so those are the first two questions answered immediately, but what about the image? Remember, the image of t is the set of y, or t sub a, sorry, is a set of pairs of numbers, vectors y and r2, such that y equals ax for some x in R2, right? So I could have said y equals t of x here, but it's gonna be more useful to think of it in terms of the matrix, right? Because basically, if we take this and write it, it's really the augmented matrix, right? So we really want to start with the augmented matrix. 5, 3, 3, 2, augment it with a generic y1, y2. And then if we want to think about, so the question is like, which pairs of y1, y2 lead to a consistent system, right? Because that's what we're trying to do here. So which y equals y1, y2 lead to a consistent system, because that will mean we can find x1 and x2 that make this work. But here, if we row reduce, I think you can tell, because the columns are certainly linearly independent, that this is going to row reduce to something that looks like this. And that is always consistent, right? Because there's a pivot in every row. It's impossible to get an inconsistency. And that means that it's consistent no matter what y is. And that means, in fact, that the image is every y. It's all of R2, right? So thus, the image of T sub A is all of R2. I could just say R2, but I'm trying to make the point that it's all of R2. By the way, there's a terminology I just want to go ahead and mention here. So such a map, so like T sub A, where the image, remember that's another synonym for range, the image is the entire codomain, the whole codomain. There's a terminology for this. It's called onto. This is the word. That map is called onto because basically everything in the codomain gets hit by the map, right? It's like, I mean, there's ways to think about this where it's like we have a copy of R2, we have our map T sub A, we have our codomain copy of R2, and it's sort of saying like, you know, if we start with some point over here, and that's X, and then it maps to T sub A of X over here, you know, that's this point, then this is saying that basically every point gets hit. So it's really like every single point in here gets hit. And so that's what it's onto. It maps onto the entire space, R2. Okay. Let's look at another example. I want to just change example A slightly. I'm just going to change these two numbers from 5 and 3 to 6 and 4, because you'll see it's leads to quite a different answer. So example B. So T sub B of x1, x2 is 6x1 plus, I forgot already, plus 3x2, 4x1 plus 2x2, and that's y1, y2. So again, the inputs and outputs are both two-dimensional. So we can write this as this map from R2 to R2, and T sub B of X is the matrix B times X, where B is just, the first column is 6, 4, second column is 3, 2. Okay, so again, answers to the first two questions I'm going to answer easily. But now let's think about the image, right? I want to do the same thing. I want to take this augmented matrix, augment it with a generic column and row reduce it. And here's the thing, I claim, you can sort of see that the columns now are not linearly independent, right? 6, 4 is twice 3, 2. The same sort of ratios going on here. So I think if you row reduce this, you actually get something like the following. So y1 there, and you get y2 minus 2/3 y1 here. Okay, so this is not always consistent because of there being a 0 row in the reduced coefficient matrix. There being only one pivot. So we need y2 to equal 2/3 y1. And so in fact, in order for, we need y2 to equal 2/3 y1 in order for the vector y to be in the image of T sub B, right? Another way to think about this is you would need y to equal y1 2/3 y1, which is y1 times the vector 1 2/3. And you could scale this up, right? I mean, I could scale this. I want to say that I can actually say that the image, so the image of this transformation is in fact just the span of this vector. But since it points in that direction, you could scale it by anything. So it's even the span of the, if I scale it by 3, it's the span of that. So actually the image now, if we have, let me just draw these pictures again. If we have something like this with our domain copy of R2 and our codomain copy of R2, then we got the span of 3, 2. We got some line through the origin. It's basically sloped 2/3, right? So it's something like that, maybe. So every point that starts over here, you know, if I pick any point over here as my X, it's going to land, well, that looks like the origin, which was not my intent. Let's try that again. It's going to land, you know, on this line. And so in fact, every point ends up landing on this line. And so that's the image. So the image is not all of R2. And this is really a nice way to describe the image right here as the span of this vector. Yeah, so this is not onto, by the way, using the terminology from before. Okay, good. Hopefully that's starting to look a little more interesting. Remember, this is the domain, and this is the codomain over there. Okay. Okay, let's do an example where we actually change dimensions. So I'm just going to do one more example sort of thoroughly, and I'm going to give you one last example after that, ask you to do your sort of yourself. Here's an example. Let's start with a pair of numbers again, but let's have that output a triple of numbers. The triple numbers are x1 plus x2, 2x1 minus x2, and 3x2. Okay, so there's your transformation, your third transformation. If I go ahead and write that this is sort of the output vector y1, y2, y3, you can see pretty much instantly that this is a map where you're plugging in 2 numbers and you're outputting 3 numbers. So it's a map from R2 to R3. And what about the matrix? Well, I'm going to write it a certain way just to really illustrate all the different ways we have to think about stuff here. So we can rewrite this especially when I sort of organize it a little bit in columns like that. You can think of this as the vector x1 times 1, 2, 0 plus x2 times the vector 1, negative 1, 3, right? Basically taking the coefficients of x1 here, and that's 1, 2, and 0, and that makes that vector. And the coefficients of x2, 1, negative 1, and 3, and that makes that vector. And then we can do that thing where we write this as matrix times vector, right? And so there's your matrix right there. It's basically the coefficient. I mean, it's maybe I'm adding an extra step you don't think is necessary. I'm just basically taking the coefficients 1, 2, and 0, and the coefficients 1, negative 1, and 3 right there. So, and then making these matrix out of that. So in fact, this matrix right here is C, the matrix C, right? So T of X is CX. Notice it's a 3x2 matrix, and we're mapping from 2 dimensions to 3 dimensions. So there is something here that this is like 3x2, but this is from 2 to 3. There's kind of a reversal thing because you need to multiply a 3x2 by a, oh, geez, Louise. you need to multiply a 3 by 2 by a matrix with 2 entries, because you need the number of entries here to equal the number of columns here, right? Okay. Now, what about the image? Well, in some ways, I claim we just sort of answered it. There's a nice way to say the image, right? Because I'm saying by rewriting things this way, you can actually see something kind of nice here. The image of T sub C, remember we give this definition, right? It's the set of all y in R3, because that's the codomain, such that y equals T sub C of x for some x in R2. But I could rewrite that as the set of, let me just rewrite this a little more explicitly, right? I could also say it's the set of everything of the form x1 plus x2, 2x1 minus x2, 3x2 in R3, where x1 and x2 can be any real numbers, right? That's kind of just sort of writing a different way of just saying, well, this is what every possible output you could get is of this form. So every time I pick an x1 and x2, I get some numbers here. That gives me a 3D vector, and that's in the image. So, so that's the way to write that. But then if we rewrite this the way we just saw, if I write this as x1 times the vector 1, 2, 0 plus x2 times the vector 1, minus 1, 3, we're all kind of like allowing x1 and x2 to be any real numbers. We've seen this set before. This is actually the span of these two vectors. And so this is kind of a neat thing to notice, that, little exclamation point there in parentheses, that, let me just maybe circle this, that this right here equals this. And these vectors are the columns of the matrix C, right? So in fact, this is a true statement in general, that in general, given T, a general transformation T of x equals AX, the image of T is actually the span of the columns of A. Let's write it this way. Okay, this is a general fact. It's worth noting. And it comes from that exact argument that I just gave up here, which is you can kind of rewrite, you could just rewrite the image like completely explicitly as a set of things of that form, which is a set of these things of this form, which is exactly all linear combinations of those two vectors. So that's a span. Okay, you could also do the thing, so notice the span is only two-dimensional. So, right, because it's two vectors that don't point in the same direction. So the span is 2D. So the image is 2D. So it can't possibly be all of R3, because in that case, the image would be three-dimensional. So this is not onto. In fact, the image is a plane through the origin, so, which I'm not going to try to draw, but you could imagine there being a very similar picture to like this picture in 3D, where you sort of have all of 3D, oh, sorry, actually this is from R2 to R3, where you have a two-dimensional space kind of like being glued into three-dimensional space somehow as a plane, but I'm not going to try to draw it because it would be terrible. You could find the equation of the plane in the same way that we've done before, where you sort of augment with a generic column and row reduce, kind of like in example B, which we did as lower dimensional case. But you could find the actual equation of the plane if you like, but I'm not going to do that here just because we've done it before. But it's a fun exercise, you know. Maybe I'll put this exercise for you, for the reader, or the watcher. Find the equation of the plane. It's right here. I'm saying is that this is a 2D plane sitting in three-dimensional space. So find the equation of the plane. Which is the image of T sub C. Okay. Okay, and then finally, as a last exercise, last example, I'm just going to write this down, and then I want you guys to think about it. So here is a map. We went from 2 dimensions to 2 dimensions, we went from 2 dimensions to 3 dimensions. You could go from any dimension to any dimension. So let's go from 5 dimensions down to 3 dimensions. So that's 5. That's a 5 tuple right there. Let's just define it to be this: x1, x2 plus x3, x4 plus x5, right? These are all just linear combinations. Linear, yeah, of the variables. So this is a linear transformation. And I guess my questions are, one is, again, it's the same questions as before, right? That I want you to think about. One is, this maps from, you can really just eyeball it, just look exactly at the picture and you can see what dimensions this goes to. 2 is, what is the matrix? That's kind of it's not tricky, I don't think, but you might think about what size the matrix is and then what the entries are. So for what matrix D? And then 3, what's the image? Is this map onto? Does it actually map onto the whole codomain? Okay, so try that on your own and maybe answer that for yourself, and then yeah, I'll stop there.